Good afternoon, everyone. My name is Abdul Aziz Aliyu, and I'm with the IEAGHG. It's my pleasure to welcome you all to this webinar. We will be presenting the findings of an IEAGHG study conducted by ERM on electrolytic hydrogen and how that compares with CCS-abated hydrogen on a cost and environmental perspective. But before we dive in, I would like to spare a moment to say a word or two about the IEAGHG. Right. So we are a technology collaboration program and are part of the RES Energy Technology Network. However, we are functionally and legally autonomous. Therefore, views, findings, and publications of the IEAGHG do not necessarily represent the views or policies of the IEA Secretariat. About the IEAGHG, IEAGHG drives global research and innovation in CCUS and CDR projects worldwide. And for more information on our activities, you can kindly visit our website. So this slide highlights the executive membership of the IEAGHG. Our members represent a diverse mix of government and industry. The collective expertise and commitment of the IEAGHG membership ensure our research remains globally relevant and technically robust. And we would like to extend our sincere thanks to all our executive committee members for their continued dedication to advancing CCUS and CDR on a global scale. For the benefit of time, I will just highlight a couple of key activities shown on this slide. We have published more than 360 technical studies, authoritative peer-reviewed reports that cover the full CCUS chain from capture to transport to storage, and also monitoring regulations and so on. We also coordinate several international networks and support regulatory development. Importantly, we are the custodians of the GHGT conference series. This is the world's largest and most recognized CCS event. The next one, GHGT 18, will be held in Perth in Australia in October 2026. Call of abstracts open in September 2025, and we encourage your participation. Next slide is a quick highlight of our upcoming conference, which is the PCC-8. We are pleased to announce that the 8th Post-Combustion Capture Conference will take place in Marseille, in France, in September 2025, hosted by TotalEnergies. PCC is the leading global event dedicated to post-combustion CO2 capture, bringing together researchers, industry experts, and policy makers. Early bird registration is open with discounted rates for students. We look forward to welcoming you in Marseille for what will be another impactful and engaging event. So in terms of this study, analysis of electrolytic hydrogen technologies with a comparative perspective on low carbon CCS-abated hydrogen pathways, this study was based on 3 primary goals. 1, to evaluate and compare the techno-enviroeconomic performance of electrolytic hydrogen against CCS-abated hydrogen, to assess the implications of large-scale electrolysis on global water resource, and to examine the potential value and utilization opportunities for oxygen co-produced through water electrolysis. So we would like to extend our sincere thanks to all the expert reviewers who contributed their time and insight to this study, and their feedback has been invaluable in ensuring the quality, clarity, and robustness of this study. So joining me are Tom Houghton, and Jonathan Long. Tom is a consulting partner at ERM. Jonathan is a senior consultant at ERM. Tom and Will be walking us through the findings of the electrolytic hydrogen study, and we are very pleased to have both of them with us. And thank you for being here, Tom and Jonathan. So before we begin, just a few quick housekeeping points. We will have a dedicated Q&A session in the final 15 to 20 minutes of the webinar. And I encourage you all to post your questions in the chat and get involved in the discussion. This session will be recorded and will be made available on our website for those who wish to revisit it or share with your colleagues. Right. So without further ado, let's get started. It's my pleasure to invite Tom and Jonathan to take the stage and walk us through the key findings of this study. Tom, Jonathan, the stage is yours.
Thanks very much, Abdelaziz. Very kind introduction. I'm going to say very little at the beginning or indeed throughout this presentation. Jonathan very kindly is going to do the bulk of it. But I'll say a few words at the beginning. So as Abdelaziz said, I'm a consulting partner here at ERM and lead our work in the hydrogen space. Jonathan sits in that same team, which we call Low Carbon Energy Solutions, where we provide a variety of strategic advisory work for our clients, both industry, governments, SMEs and NGOs. And if you want to find out more about ERM and what we do, you can jump to our website, or we'll flash up our email addresses at the end of the presentation. If you want to take a note of those and get in touch, we'll be very welcome to do so, and we'd be very happy to speak with you. So in terms of what we're going to be doing today, Jonathan, if you could just jump to the next slide. We'll just do a quick intro to the scope of the report. Abdelaziz really has covered that mostly, so I just want to point out a couple of little aspects of detail of what's in there. Jonathan will then take us through the main findings, and then hand back to me to run through some recommendations that came out of the study that we conducted. So Jonathan, if we can just go to the next slide. So as Abdelaziz said, this is really a techno-economic study looking to assess both the economics but also the greenhouse gas emissions associated with different electrolytic hydrogen production pathways. We looked at two target years, 2030 and 2050, and we took one country as our kind of case study country, if you like. So that we chose the Netherlands because this is a key hydrogen hub, as many of you will be aware. So that's just a little bit more detail on the overall kind of direction for the study. We had a number of key objectives set out. This is a little bit repetitive of what Abdelaziz has just said, but with a little bit more detail. So we really wanted to be able to provide this comprehensive and comparable techno-economic and emissions assessment to allow there to be this kind of set of data out there that other researchers, other bodies interested in assessing this area could use as a form of benchmark, and it allowed us to compare these different means of producing hydrogen through electrolytic means, different technologies, which we think's not really been done in a great deal of detail previously. Importantly, we wanted to compare this with other low carbon hydrogen production approaches notably CCS-abated hydrogen from natural gas, so blue hydrogen, to use the common parlance. And we think that this set of data should help to facilitate that benchmarking with other low carbon production technologies. So that I'd say is the core really of the work that we did. There were, alongside that, some other aspects which were looked at to a perhaps a slightly lesser degree from a detailed perspective. What about the impact of electrolysis on water consumption and water scarcity? As many of you will know, this is an issue that is rising up the agenda for many, particularly as we talk about producing electrolytic hydrogen in places around the world that already are subject to water scarcity and water stress. We also made a study of the effect that hydrogen consumption could have on water vapor emissions, and particularly at high altitude. So, for example, if we were using hydrogen in aviation. Again, this is an under-researched area and worthy of some more attention as we think about the prospect of using more hydrogen in the energy system. We undertook a study to look at the value or the valorization potential for oxygen generated through the production as a or byproduct from hydrogen production, and looked at the potential industrial applications that we could apply this to. Again, a somewhat under-researched area, and one which could have some interesting impacts for the business models for hydrogen producers. And finally, we did some work around looking at hydrogen leakage during production distribution. As some of you may be aware, there is concern about leakages already, of course, in the natural gas network, and the impacts and the global warming potential that this has. Hydrogen, whilst it's not a greenhouse gas in the same way that methane is, or CO2, of course, but it does have the potential to generate, particularly at high altitude, global warming potential, and again, under-researched area that we wanted to look at in a little bit more detail, so that we could assess the potential impact that could have. So, as I say, just wanted to provide a little bit more detail on some of the objectives of the study, as compared with the kind of high-level view that Abdulaziz presented just now. But with that, I'll hand over to Jonathan. He's going to run us through the majority of the content. I'll pick up at the end, as I mentioned, and also I'll be taking a look at the questions as they come in. I do, as Abdulaziz said, encourage you to put questions in the chat, and we'll do our very best to answer them. Of course, if they're questions of detail, we may have to refer you to the study or get back to you with responses. We may not be able to answer everything here and now, but we'll do our very best. But so with that, I'll hand over to Jonathan. Jonathan, if you'd like to give a quick introduction to yourself, including the fact that you're in fact now a managing consultant at ERM, having been recently promoted owing to the very good work that he's been doing with the team. So over to you, Jonathan. I'll go off camera for a bit, but come back on when we get to the end of the presentation.
Cool. Thanks, Tom. Yeah, that's very kind. Yeah, so I'm Jonathan Long. I'm a managing consultant at ERM. I specialise in hydrogen. So, I mean, as Tom mentioned, we conduct techno-economic studies, funding acquisition support, market studies, all focused on hydrogen and derivatives. And we look at production as well as transport and storage and end-use applications. And prior to ERM, I was working as a process engineer in various design and operations roles in the industrial gas sector, and I'm a chartered chemical engineer. So that's my background. I'll I'll get straight into the presentation then. So I'll just start by building on a couple of points that have already been made, introducing a couple of the modelling conditions for additional context, and then we'll go straight into some of the key findings. So as mentioned, we constrain the study to a single country, the Netherlands. So there are a few reasons for this. The Netherlands has both electrolytic and carbon capture enabled hydrogen production projects in development. It's also already a major producer and consumer of hydrogen, particularly at the industrial hub in Rotterdam. And for practical reasons, it aligned with a previous study carried out on blue hydrogen pathways in the Netherlands. So that allowed us to draw comparisons more easily, which increases the value of our findings here. We looked at several electrolysis and natural gas processing technologies. So I'm going to refer to these as green and blue respectively. I know the colour classification isn't favoured by everyone, but for simplicity, I'm going to refer to our electrolytic pathways as green and our natural gas processing pathways as blue. So we looked in depth at alkaline, PEM, and solid oxide electrolysis, SOEC, with some review of AEM and other innovative technologies. But the focus was on alkaline, PEM, and solid oxide. Alkaline and PEM for their maturity, solid oxide because of its strong potential in certain applications and higher efficiency. And for blue hydrogen production, we looked at CCS-enabled steam methane reforming, an electric version of that. We looked at autothermal reforming and also partial oxidation reactors. Again, some more niche technologies were touched on in the study for blue hydrogen production, but they're low maturity, so we didn't go into depth. For green, for electrolytic hydrogen production, we looked at 3 electricity scenarios, which can totally change project economics and emissions. So our grid-powered scenario assumes the electrolyser was connected to the grid with high availability, maximum availability. Our renewables connected scenario assumed direct connection to renewables and a 50-50 split of wind and solar, with power generation profiles modelled on the conditions of the Netherlands. And the third scenario is use of curtailed electricity from offshore wind, again modelled for conditions in the Netherlands. So in this scenario, the electrolyser could only operate on power in surplus to demand, which, as you can imagine, results in a fairly low utilisation. So these are a few more details about the study approach. I'll go into some key findings now then. So starting with a focus on electrolytic hydrogen, we're looking at 2030. We found that the renewable connected scenario was lowest cost across all electrolyser technologies. So the chart has levelized cost of hydrogen, LCOH, on the y-axis, and the 3 different electrolyser technologies are along the bottom. Each we've got their different electricity supply scenarios for each technology. So when grid connected, the load factor is highest, as I mentioned, of the 3 scenarios. So the hydrogen production volume is highest, but the project is exposed to grid power price and any grid connection fees that come with that. So it isn't the lowest cost. When using only curtailed electricity, the electricity cost component is lowest, but so is the load factor. So modelling showed that the electrolyser was productive for between 11 and 24% of the days of the year for the different cases we studied. So hydrogen production then is lowest of the 3 scenarios, and that results in a very high levelized cost. So the capex for the electrolyser is fixed, so low utilization and therefore low hydrogen production results in that high levelized cost. In the renewable connected scenario, the load factor was high for all of our modelling, greater than 90% for all of the scenarios. And there's no exposure to those additional grid fees. So this one's coming out at the lowest cost scenario. We also found that you can see on here, we found that alkaline technology was lowest cost. That's driven by having the lowest capex of the 3 technologies due to maturity. Again, we're looking at 2030 here, so that applies to 2030. And while solid oxide electrolysis achieved a lower electricity cost, achieves that through improved efficiency, this was generally offset by the additional cost of heat required in this particular case we're showing. So solid oxide electrolysis requires a steam feed rather than ambient temperature water. So there's a cost associated with that. Now looking at how we expect the costs to evolve from 2030 through to 2050, we're just looking at PEM electrolysis here for comparison on the charts. The bar chart on the left is for 2030 and the one on the right is for 2050. Do note the change in scale on the y-axis. So we're 0 to 40 on the left and we're 0 to 8 on the right. So it does represent a significant reductions. We expect to see reductions in levelized cost, mostly driven by a drop in capex. So this trend is similar across all three electrolyzer technologies, alkaline, PEM, solid oxide. It's slightly less pronounced on alkaline because it's most mature currently, and more pronounced on solid oxide, which is currently least mature. As I say, we've got PEM here, which is somewhere in between. There are particularly strong savings in the renewable connected scenario, taking full advantage of that capex reduction. So in that scenario, seeing at least halving from 5.7 to 2.6. The electricity cost component becomes the driver in 2050. In the grid connected scenario, electricity is expected to remain high cost. So the overall levelized cost saving is mild. Whereas for the renewable connected scenario, we see benefits of the capex reduction. As I say, that levelized cost has roughly halved, slightly better than that. As the electricity cost share increases, of course, electrical efficiency becomes more important, and so this is the point at which we expect high efficiency technologies to become, increasingly important, increasingly compelling. The curtailed scenario suffers from a very high levelized capex, as we kind of already touched on, again, due to low utilization, low hydrogen production in this scenario. There is a major saving between 2030 and 2050 due to the capex reductions we expect, but it still comes out as the most expensive scenario by far. So here we're looking at a comparison between blue and green hydrogen production costs. The graph, again, it has LCOH, levelized cost of hydrogen, on the y-axis, and the different technologies are along the bottom. For the electrolytic technologies on the left, we're showing the three different electricity scenarios, and this chart's for 2050. So currently, today, green hydrogen struggles to compete with natural gas-derived hydrogen on cost due to high electricity prices, cheap natural gas prices, and lower maturity technology. In 2050, however, we do see a scenario where green hydrogen can compete with blue hydrogen for some technologies and scenarios. So green hydrogen on a renewable power generation scenario could compete with either the electric SMR or CCS-enabled ATR processes, possibly with the standard CCS-enabled SMR2 in some cases. I mean, it isn't much more expensive than that. And any of the electrolysis technologies would achieve this low cost when directly connected to renewables, alkaline, PEM, or solid oxide. The grid connected or curtailment scenarios are still not expected to be competitive with blue. They're either exposed to the high grid power prices, electricity prices, or simply not producing enough hydrogen to drive the levelized cost down in the case of the curtailed scenario. Clearly, the sensitivity is that electrolysis will be exposed to the electricity price, whatever source that might be, and blue hydrogen will be exposed to the natural gas prices. For green hydrogen, of course, the bulk of the cost is electricity here. For blue, the bulk of the cost is natural gas. There's also a carbon price cost component for blue hydrogen here, which might drive costs up in the future. The price is acting on the small portion of carbon that the carbon capture unit fails to remove. It's not removing 100% of the carbon. So now we're comparing emissions intensity of the hydrogen produced by the various pathways, looking at green and blue. So on this chart, along the bottom of the different pathways, green production on the far left, blue on the right. And again, we have a few different electricity source scenarios represented for the green production pathways. Grid on the far left, followed by renewables, RES. And this graph is for 2030. So clearly, without carbon capture, natural gas processing is significantly more carbon intensive than electrolytic hydrogen, typically 3 or 4 times as much for these cases. That's represented by the bar in the middle, SMR with no CCS, but also the hatched bars represent the portion of carbon emissions that are captured. Interesting to note that all of the core natural gas processing pathways, CCS-enabled SMR, ATR and partial oxidation, and the ESMR, they all have similar or slightly lower carbon intensity product than the grid-connected electrolysers for all the electrolyser technologies. Quick note about the solid oxide electrolysis. As I mentioned, it requires a feed of steam, not of ambient temperature water. In the study, we assume this is provided by natural gas combustion, that the heat required is provided by natural gas combustion. So this has the highest associated emissions. These are the emissions you see for the direct connection to renewables that you see, RES. So this really indicates a worst case for solid oxide electrolysis, and there are options for improving on this if decarbonised heat sources were used. And then solid oxide would drop to be in line with the other electrolyser technologies, if not slightly better from the slightly better efficiency of the technology. A key factor with the blue hydrogen technologies is the assumed capture rate that I touched on. So for our study, we applied something between 90 and 98%, depending on the technology, which is pretty strong. There are ultra high capture rates in development, which achieve 99% capture rates. That comes at the cost of increased electrical consumption. In our study, we found that from an emissions perspective, this trade-off actually works out. It's worth using grid electricity to increase the carbon capture rate if your overall target is to decrease overall emissions. The grid-connected electrolysis, for that to compete, the carbon intensity of the grid electricity, of course, is critical. Again, here, this is for Netherlands, and we're looking at 2030. There are also regional nuances to grid intensity that are not brought out here. So location within a country may even impact the emissions associated with grid-connected electrolyser. Looking forwards in 2050, we expect the grid to be decarbonised, and so the carbon intensity approaches that of renewable power sources, and then of course that's very low, clearly lower than blue hydrogen. It's not a given that the grid will be fully decarbonised in 2050 though, so the comparison between blue and green hydrogen emissions intensity might remain quite close in the medium to long term. But provided the grid does decarbonise, electrolytic hydrogen will be capable of producing the lower carbon intensity product, but currently carbon capture can compete with the carbon intensity of the grid. So once the hydrogen is produced, it needs to be transported to wherever it's used. Here we're showing the carbon intensity of different hydrogen transportation options. We have ammonia, where the final product is ammonia. We have ammonia cracking, where conversion to ammonia is followed by reconversion back to hydrogen. And we have liquid hydrogen, we have compressed gas pipeline, and methanol, where methanol is the final product. So you'll see that there's not a reconversion component to the methanol there. And it's shown for green hydrogen production from an alkaline electrolyser using grid electricity in 2030. So ammonia production has a high carbon intensity, and that's seen in both the ammonia case and the ammonia cracking case. The cracking process also has a high carbon intensity if reconversion back to hydrogen is required. There are options to reduce that intensity by cannibalizing the low carbon hydrogen produced in the process to provide the heat required for cracking, but that comes at a cost of product recovery. It's not a very economical use of the hydrogen, but benefits on emissions. For liquid hydrogen, the production emissions, the conversion emissions are associated with the power required to liquefy hydrogen, which is quite demanding. There's also a large portion associated with storage due to expected boil-off losses. We don't see that component with the other transportation and storage options, which don't suffer those boil-off losses. Transferring hydrogen as a compressed gas through pipelines has the lowest intensity, doesn't require any processing. There are compression costs associated with that, which have an associated carbon intensity from the electricity for it. That is shown, but it's barely visible on this scale. And finally, methanol has the highest intensity of all of the processes, mostly because it requires a feed of CO2. So this transportation method is exposed to the carbon intensity of however you source the CO2. So the key message here is that moving hydrogen from where it is produced to where it's needed can add a significant portion to the carbon intensity of the product. But it's not always as simple as choosing and committing to the lowest intensity route. There might be practical or economic reasons why one is favoured over the other. So moving away from carbon emissions and levelized cost, I wanted to bring out a couple of other findings, firstly on water consumption of electrolysis and then on oxygen valorization and what can be done with the oxygen byproduct of electrolysis. So stoichiometrically, producing 1 kilogram of hydrogen by electrolysis requires 9 kilos of water feed. Due to actual efficiencies, this might be more like 10 kilos of water. That's 10 kilos of ultra high purity water fed to the electrolyser. The requirements on water purity are very stringent. So there will always be a water purification step prior to the electrolyser. The demand on that purification step and therefore the losses will depend on the water source. But here we're showing tap water, which is relatively clean. And you can see that 20 kilos feed is needed to produce 1 kilogram of hydrogen. Seawater is often explored as the water source for water scarce regions. That requires desalination, which is mature and it's well established as a water treatment process. It's relatively low cost. It adds proportionally little to the overall power required for producing hydrogen compared to the electrolysis process itself. The main challenge or criticism is that effluent from the process needs to be treated very carefully. Also, depending on the configuration and cooling requirements, cooling water will also likely be needed by an electrolyser plant. That could add more than 10 kilograms of water per kilogram of hydrogen produced. I won't discuss that in any more detail here. As I say, it varies between plants, but it should be mentioned that the feedstock water for electrolysis is not the only water required by the plant. Now, thinking about oxygen valorization, high purity oxygen is produced as a byproduct of electrolysis of water. By mass, you get 8 times as much oxygen as hydrogen produced, and so the question often comes up as to whether this product can be sold to improve project economics. For context, the existing oxygen supply chain is very mature, it's very well established. There are lots of applications for oxygen: water treatment, combustion processes, petrochemicals, food, healthcare. Currently, there are various options for procuring oxygen depending on the volumes and purities that you require. And it can be produced at very high efficiency, very high volumes, and low cost currently. There are a range of bulk liquid and compressed gas delivery options as well, which is not dissimilar to hydrogen products. So this is the existing supply chain that electrolytic oxygen must compete with. So oxygen from an electrolyser will, as a minimum, probably need drying via an adsorption process, and then likely also needs compression depending on the application needs. So there is some additional processing required there, but not too much, and both of those technologies are mature. However, because of the maturity of the existing market and supply chain, we only see electrolytic oxygen really being interesting when co-located with a demand, and when local existing oxygen sources are either non-existent or sold out. It's going to be very difficult to compete with well-established incumbents that are supplying oxygen locally at low cost. So the message is, I think, don't assume that you can sell the oxygen to improve your project economics. There will be examples where this will work and it will be very beneficial, but it's not a given in all scenarios. The important factors are proximity to an oxygen demand and strength of the local oxygen production competition as well. So that's a detailed look at some of our key findings. I'll hand back to Tom now to talk through some recommendations. Tom, back to you.
Thanks, Jonathan. Yeah, so when we were commissioned to do this study, there were two kind of key areas that we were asked to look at in terms of recommendations from the findings of the report. So obviously the findings in themselves are important, and here what we're doing is saying, okay, we've learned this. What does this tell us about where we should direct research going forward? Do we think, where are there still gaps in our knowledge, having conducted this, and also, are there aspects of policy that we might want to think about and adjust in order to get the sort of outcomes that we want to achieve in the 2030, 2050 time frame? So this is how the recommendations are organized. But there is also, of course, in the report a summary of those findings, both in an executive summary and a set of conclusions. So the first thing, I think, from an R&D perspective, as we've emphasized throughout, this was a single country study. That was for a very good reason. I think we've tried to highlight what those reasons were, the ability to provide that kind of comparative picture relative to some work that had been done previously, and also to pick a geography where there is and has been an expectation that there could be significant hydrogen activity. However, we know that there is variation across geographies, and understanding how the picture might look different in other locations would be certainly something that would be worthwhile. It wouldn't necessarily change all the parameters by any stretch of the imagination, but understanding how much variability there is would be useful. When we did the research on fugitive emissions, and I see there's a question in the chat about this, which we'll come back to, but we wanted to do this kind of initial analysis on what the extent of emissions were, fugitive emissions were from the production and transport of hydrogen, and what we discovered is that this really was very much an under-researched area where there was little data available to support the analysis. So we think that some actual monitoring and direct analysis of those hydrogen emissions is going to be important. It's interesting that with our current pipelines, natural gas pipelines, this is something which is not measured and monitored in any way like a systematic way. And we feel that there's an opportunity as we transition to the use of hydrogen, green hydrogen, that to get in early and to really start and look at this so that we know what we're looking at. We know what the potential is for this to have an adverse effect on climate change. Similarly, it remains distinctly under-researched, the impact of water vapor, especially at high altitude. Of course, the combustion of fossil fuels is already producing significant amounts of water vapor today. With the combustion of hydrogen or the use of hydrogen in fuel cells, the product is water as well, and really understanding what the relative balances of water vapor production are is important. I mean, it's easy to do it on a stoichiometric basis, but we need to understand what the reality is, and we in particular are interested in understanding what the impacts at high altitude are if hydrogen is to be used, as some suggest, as the most viable long-term fuel for real zero emissions aviation. So again, we think some more research looking at that would be important. Valorization of electrolytic oxygen. I think there's a little bit of work to be done here around whether there are markets that exist today or which are potential markets in the future where we could see cases where it would make more sense to capture that oxygen and to reuse it. As Jonathan mentioned before, there is an established and mature oxygen market out there. There is a lot of talk about oxycombustion as being a means to improve overall GHG emissions from all sources by more efficient combustion processes. So I don't know whether that, for example, might create some new markets that we might wish to exploit. Although it has to be said, of course, that the oxygen that comes out of the electrolyzer is very pure and and can be used directly in higher value type of markets. But those are markets which are already pretty crowded with existing suppliers. We think there is more work again to be done around the broader environmental impacts. The shift to using hydrogen will require the building of significant amounts of infrastructure, which has the potential to impact on land use, so land use change. There is also significant embodied emissions in that infrastructure. And so whilst it is true to say that, again, hydrogen infrastructure is going to be replacing existing infrastructure used for the processing of fossil fuels today, we need to properly understand what the extent of that is. And then finally, one other area of research we think important, this modeling of optimal electrolyzer size relative to renewable generation. So one of the criticisms that we hear of hydrogen recently is that in order to use your electrolyzer most efficiently, you want to oversize your renewables, but nobody is going to be very happy to see large tracts of renewables being built which are being underutilized, even if that is the most cost-effective solution. So understanding how to optimize across the whole chain using storage, optimal sizing of the different components is going to be important. Quickly turning to the policy side, we think that more collaboration, more international collaboration can be helpful in terms of driving down the cost of hydrogen production, so sharing of information, but also looking at ways to produce hydrogen in the most cost-effective places and use that hydrogen perhaps in those same locations, if that makes sense, if the products are easy to make in those locations and can be shipped more easily than hydrogen, or on the other hand, bringing that hydrogen to where it can be used most effectively. If you think about steel, for example, you kind of want to make steel where the iron ore is. Ideally, if you're thinking about H2DRI, do you want to actually relocate your blast furnaces to where the hydrogen is, or do you want to continue to have that where the supply of iron ore is? And optimizing across that through an international collaboration would be very useful. We need harmonization over GHG methodology. We see this across the piece in renewable fuels, whether it be hydrogen, whether it be biofuels. There is a lack of harmonization of these GHG methodologies, and having clearer pictures is going to facilitate trade. It's not only going to facilitate trade in physical hydrogen, but it also facilitates the trade in certificates associated with that hydrogen. So this is really important. So guarantees of origin and getting certification sorted and commonality between different systems will really help with a more efficient hydrogen system. Encouraging and accelerating renewables, clearly important. And this is underpinning all electrolytic hydrogen production. We need more renewables. We need to see that continued development of renewables, whether it's for electrification, pure electrification, or for the generation of hydrogen and hydrogen-derived fuels. We also are very keen to see a harmonization, and this links back into the sort of global GHG methodology, this kind of harmonization of the way that different hydrogen is classified. We don't really like the color taxonomy. It's not particularly helpful always. What we need is a measure of GHG emissions and carbon intensity of those hydrogens so that people can make informed choices as they think about their decarbonization journeys over what kind of hydrogen they want to use in their system. We think there's ongoing need to improve electrolyzer technology, but also really important, improve electrolyzer manufacturing technology to drive down cost and to increase performance. So one of the things that concerns me a little bit about too much innovation in electrolyzer technology itself is that you kind of get distracted from the real goal of driving down cost. But certainly innovation in manufacture would be really helpful. Similarly to that, standardization across technologies will also help drive down costs. And finally, support for carbon pricing. None of this really happens without there being a recognition of the cost of carbon in the system, the cost of carbon produced by the combustion of fossil fuels. And we need to see the support both in terms of, yes, okay, subsidies for the hydrogen, but also a recognition and a full cost picture for fossil fuels that will help with the competitiveness of hydrogen across the range of applications it's used in. So with that, I'll conclude our presentation. Sorry, we don't have a huge amount of time for questions, but we're very happy to try and take some of the questions that are in the chat or others that might come up. And you can see on the screen there our email addresses if you want to get in touch. So I wonder if perhaps I can start by looking at some of the questions in the chat, and I'll have a go at a couple of these, and perhaps hand over to Jonathan as well to answer some of them. Although I should say that quite a few are real points of detail, and I'm not sure that either of us are fully equipped to answer exactly on that detail, and we will be giving you the link to the report at the end of the presentation. Abdulaziz will be doing that, so you can have a look at that and see absolutely all the detail. There was a general question from Mahbub, and thanks for that. Yes, this is a really good point. The question about what are the assumptions around electricity costs? What's that based on? What countries are in the process as we speak of reviewing their low carbon energy transition pathways, and how confident are we of the assumptions in the study? Well, I mean, one thing is for certain. Any assumption that we've made is going to be at heart wrong. We know it won't be exactly how that turns out in the Netherlands or anywhere else. We feel that our assumptions are pretty robust and reflect best knowledge at the time we conducted the study. However, we are acutely aware that there are significant changes happening out there in terms of those transition pathways, and that will have an impact on the cost of electricity. Also, of course, the availability of renewable power for hydrogen and hydrogen derivative production. However, I guess what I would say is we have conducted sensitivity analysis around our core assumptions, which gives us confidence that we can take a look at the broader picture through that. But this remains a risk with any study of this nature. Things change, and things are changing very fast right now. And undoubtedly, some of the assumptions that we have in our study will be out of date already, but the sensitivity analysis should help to address some of that. There are a couple of points of detail around costs of steam for SOEC, around cost down for electrolysers and associated balance of plant efficiencies and so on. I'm not sure, Jonathan, I guess you can see those as well, whether you can answer any of those directly, or whether we're better off pointing people to the report itself.
Yeah, I think I skimmed some of the detailed questions on this, and as you mentioned, Abdulaziz is going to share the report, and so just a signpost in there is a pretty detailed explanation of key assumptions in section 7 of that report, which explains each of the assumptions and the impact on the study as well. So I think for those particular questions, I'll refer to the report as my fairly simple answer.
Yeah. Safer that way. There's a question around CCS technology that we modelled. I think, Jonathan, we used amine based as the core assumption.
Yeah.
We did mention other technologies being available, but I think amine based was the core assumption that we used. Fugitive emissions, I think we ignored fugitive emissions sorry, there's two questions about fugitive emissions. The first one here is about fugitive emissions from natural gas. Again, I'm not sure what was taken into account in terms of upstream emissions for the natural gas. That should be clearly set out in the report, but we would have had a natural gas emissions intensity, which would have reflected not just the embodied emissions in the natural gas, but also the emissions associated with the production and delivery of that gas. But I don't know the exact detail, but that should be clearly set out in the report. We've got a question about grid electrolysers and the huge load that they represent, and the doubt as to whether all of the power that could be provided would be clean power. I think, Jonathan, I'm right in saying that when we do our grid case, we're just assuming an emissions intensity in that given year, which would include it being a combination of both renewable and fossil fuel power. Obviously, the fossil component is much smaller in 2050. So we should be able to, just say, okay, this is, we're drawing this as is from the grid. But obviously, from a practical perspective, what a lot of developers are thinking about is having their electricity supplied through PPAs, and maybe that was what the question was sort of aiming at, saying, well, do you think you would be able to put in place sufficient PPAs to satisfy your demand? I mean, there are big questions over this. I completely accept whether we can reach the scales of demand that would be associated with some very large electrolyser facilities. However, that was not the primary purpose of the report here. It was more to think about, okay, so if kind of everything works out from a capacity perspective, what could we expect the likely costs to be? What can we expect the likely GHG intensities to be? But undoubtedly, there are some question marks over the ability of the system to supply those significant demands.
I think we're out of time.
Okay, yeah. There's some really interesting other questions. Thanks very much for those. And it's reference to the IRENA report on water cooling. That is a great report, and I would definitely urge everybody to, if anybody's interested in that subject, to take a look at it, because there's some great research and it draws on a lot of other studies as well. So with that, I'll hand back to Abdulaziz to say a few closing words.
Yeah, very well. I thought that was a brilliant summary of the study. Tom and Jonathan, thanks for the excellent presentation and engaging with the questions. I think one of the key takeaways, from this study for me is that by 2050, I think we need to acknowledge that feedstock cost will constitute the bulk of the levelized cost of hydrogen for both CCS-abated hydrogen as well as electrolytic hydrogen. And consequently, fossil fuels cost will be the primary influence for the cost of blue hydrogen. And accordingly, electricity cost will determine the cost of green hydrogen moving forward. So with that, I am pleased to share this is a big news that the final report is now published and live on the IEAGHG website, should you wish to explore it in more detail. And thanks to ERM for facilitating the delivery of this very important study. The recording of this session will also be made available shortly. Until then, thank you once again, everyone, and we look forward to welcoming you all at a future IEAGHG event. See you soon. Thanks, Tom, and thanks, Jonathan.
Thanks, Abdulaziz.
Thank you. Cheers.
Thanks all for joining.
Thanks. Bye.
Bye-bye.